Hello students, welcome to my channel. In this class, I am going to give you definition of a curvature and a torsion and prove some theorems related to curvature and a torsion. Let us start the topic. First definition of a curvature: the arc rate at which the tangent changes direction as the point P moves along the curve is called the curvature vector of the curve, and its magnitude is denoted by kappa. So dt by ds is actually the rate of change of a tangent with respect to arc length, and its magnitude is kappa. So t cap dash mod is equal to kappa. Torsion: the arc rate at which the binormal changes direction as P moves along the curve is called the torsion vector of the curve, and its magnitude is denoted by tau. So here the rate of a change of binormal with respect to arc length is db cap by ds, whose magnitude is a torsion, or b cap dash is equal to torsion. So now a theorem: a necessary and a sufficient condition for the curve to be a straight line is that the curvature kappa is equal to 0 at all points of the curve. Let us prove this theorem now. Proof of a necessary condition. We know the equation of a straight line is vector r is equal to vector as plus b, where a and b are constant vectors. Now differentiating both sides with respect to arc length s, we get dr by ds is equal to vector r dash is equal to vector a. This implies vector t cap is equal to vector a. Again differentiating both sides with respect to s, we get t cap dash is equal to 0. Then this implies kappa n cap is equal to 0 by Serret formula. Squaring both sides, kappa square is equal to 0. Squaring both sides. So this implies kappa is equal to 0, which is the required necessary condition. Then proof of sufficient part. First of all, I shall explain this, then I shall prove that one. So proof of necessary part. We know that the equation of a straight line is vector r is equal to vector s plus vector b, where h is the arc length, where vector a and b are constant vectors. Now differentiating both sides with respect to arc length s, we get dr by ds, which is denoted by vector r dash is equal to vector a. So that is t cap is equal to vector a. Again differentiating both sides with respect to s, we get t cap dash is equal to 0. But by Serret-Frenet formula we know t cap dash is kappa n cap 0. Squaring both sides we get k square, because n cap dot n cap is equal to 1. It is a unit normal vector. So kappa is equal to 0, which is the required necessary condition. Proof of sufficient part. Let kappa is equal to 0 at all points of the curve. This implies kappa n cap is equal to 0 by Serret-Frenet formula. So this implies t cap dash is equal to 0 by same formula, because t cap dash kappa n cap is equal to 0, so t cap dash is equal to 0 by Serret-Frenet formula. So this implies vector r double dash is equal to 0. So this implies dr by ds square is equal to 0. d square r by ds square is equal to 0. Now integrating both sides with respect to s, we get dr by ds is equal to vector a, where a is a constant vector. Integrating again, we get vector r is equal to vector a s plus vector b. Vector a s plus vector b, where are constant vectors. So vector r is equal to vector s plus b, who is a straight line. This proves the sufficient part of the theorem proved. This proves the sufficient part of the theorem. Here in the first part, T cap dash is equal to 0. This implies kappa n cap is equal to 0 by from a serrate-Frenet formula, because T cap dash is equal to kappa n cap. So in the first part, I mean in the necessary part, we are having dr by ds is equal to vector A, that is T cap is equal to vector A, T cap dash is equal to 0, T cap dash is a kappa n cap. This is by serrate-Frenet formula. So kappa square is equal to 0, kappa is equal to 0. Again kappa 0, kappa n is equal to 0 by serrate-Frenet formula. Since the same region, kappa n cap is equal to T cap dash. Then vector r double dash is equal to 0, d square r by ds square 0. Integrating, we are getting again integrating with respect to arc length s, we get vector r is equal to s plus b, which is a straight line. So this proves the sufficient part of the theorem. The first theorem is now proved. Let us proceed to prove the next theorem. Our next theorem is a necessary and a sufficient condition that a given curve is a plane curve is that torsion is equal to 0 at all points, and that we have to prove. Proof of a necessary part. Let the curve be a plane curve. The tangent and normal at all points lie in the plane. The tangent and normal at all points lie in the plane. So the plane is the osculating plane. Okay, let the curve be a plane curve. Then the tangent and the normal at all points lie in the plane of the curve. Plane of the curve. Plane of the curve. Plane of the curve. So the plane is the osculating plane. So the plane is the osculating plane. That is the unit binormal B cap is constant at all points that is the unit binormal B cap is constant at all points of the curve. So this implies the cap by ds is equal to 0. This implies minus tau n cap is equal to 0 by Serret Frenet formula. This implies tau is equal to 0, which is the required necessary condition. Now, proof of sufficient part. Let tau is equal to 0 at all points of the curve. This implies minus tau n cap is equal to 0. This implies b cap dash is equal to 0 by Serret Frenet formula. This implies d b cap by ds is equal to 0. So this implies vector b cap is a constant vector at all points of the curve. Now d by ds vector r dot vector b is equal to r dash dot vector b vector r dot b cap dash. So this is t cap dot b cap vector r b cap dash. So this is equal to 0. This is also equal to 0 because b cap dash is equal to 0. Since t cap and b cap are perpendicular to t cap and b cap are perpendicular to each other, and b cap dash is equal to 0. So d by ds of vector r b cap is equal to 0. This implies r dot b cap is equal to 0. This shows that the projection of vector r on b cap is 0. This implies, okay, d by ds of r dot b is equal to 0. So this implies r dot b cap is equal to constant. So this shows that the projection of r on b cap is equal to 0. That is, the curve must lie in a plane. So with this, our second theorem is now proved. The topic for today's class is completed. I shall meet you with a new topic in my next class. Till then, goodbye.